Hi everyone, I welcome you to the presentation of this lecture on a topic called Thevenin's theorem. So, by definition, Thevenin's theorem is basically, or it states that a linear two-terminal circuit can be replaced by an equivalent circuit which consists of the voltage source, which we are calling Thevenin's voltage, as well as a resistor RTH, which is the Thevenin's resistor. So the basic rule in this, you'll be given a circuit which will be two terminal circuit. It can be as complicated as it could be, but our role is basically to transform it in a way such that whatever sources you have there, we just need to see one voltage source which should be in series with equivalent resistance, which is the Thevenin's resistor, and then you connect back the load. So in Thevenin's theorem, we'll just be finding the Thevenin's voltage and the Thevenin's resistance, putting them in series, and then we connect the load if we are asked to do so. So this is the basic rule, finding the Thevenin's voltage. And in finding the Thevenin's voltage, what you basically do, if you are given a circuit like this one, you remove the load and then view your circuit from that point. So what you're viewing there, or the voltage you see in that circuit, that will be the open circuit voltage, and that will be your Thevenin's voltage. Whereas finding the Thevenin's resistance, once we remove the load from there, if you are to view your circuit from that point, a combination of resistors or the equivalent resistor you see in that circuit is what we are calling the Thevenin's resistance. So let's look at an example. This one is saying find the Thevenin equivalent circuit of the circuit shown below to the left of the terminal AB. Once we do that, then we find the current passing through the load 6 ohms, which is the RL. So they want us to find the Thevenin's equivalent circuit. So what we are doing is, in this given circuit, we transform it in such a manner that we'll just see one voltage, which is Thevenin's voltage, being in series with the equivalent resistance, Thevenin resistance. And then when we connect back the load, which is this one, we calculate the current passing through that same load. So on our solutions, what we want is transforming this circuit in such a way that we just see this Thevenin's voltage and the Thevenin's resistance. Then we are connecting back the load, which is this one. So in finding the Thevenin resistance, from the previous slide I was explaining to say you remove the load, which is this one. If you remove the load, you view your circuit in this one, but you need to switch off the independent sources. So if you look at this circuit, it has got two independent sources. There's a voltage source which is independent and the current source which is independent. So how do you remove them? You switch them off. So for the voltage source, if you switch it off, it becomes a short circuit, which is this one. For the current source, if you switch it off, it becomes an open circuit, which is this one. If you view from there, upon removing that one, this is what you're seeing. You realize that these two resistors, this one and this one, are now in series, or in parallel, sorry. So this one, a 4 ohm and the 12 ohm, these are in parallel because they have that point and both point being connected, as well as this point and that point being connected. So you have a parallel combination of this one. What we are having there, the total will be in series with a 1 ohm. So a combination of those resistors will give us the Thevenin resistance, which is a 4 ohm. With that said, we can also calculate the Thevenin's voltage. So the Thevenin's voltage will be, if you view from that point, the voltage you see there, that will be the Thevenin's voltage. So if you are viewing from there, the voltage we are seeing is basically the voltage drop here, or basically there, that will be the Thevenin's voltage. So in here, if we look at loop 1, which is this one here, you can go back to the video where I was explaining mesh analysis. I was saying in this loop, you assign polarities to the elements which haven't been given polarities. So if you look at the voltage source, which is this one, it has polarities, you leave it. You come to this one, it doesn't have polarities, so you give polarities going in the clockwise direction. The terminal you meet first, you give it positive, then the other one negative. So this one will be positive and that one negative. When you reach this one, you give it polarities positive and negative. Once you have that, then you do your voltage breakdown there. So you realize that in loop 1, what we are having is, as you are coming there, you meet 32 volts, but you are meeting it from the negative. That's why we have negative 32. You come to the 4, this will be 4 with that current, which is positive 4I. Then when you come to this one, to be the 12. So this I1 is meeting the 12 from the positive terminal. That's why you are having 12 with I1 being positive. But at the same point, there is this current here, I2, meeting this same 12 from the negative. That's why you have negative I2 there. So you are having this equation. And then when you go to loop 2, in loop 2, which is this one here, you realize that the circulating current in there is basically this same 2 amps, except the loop current in here is going like that, and the current in here is coming the other way around. So I2 is basically negative of 2 amps, which is that one. This is what you are having there. Since we have our I2 there as negative 2 amps, if you replace it in there, we're going to have our I1, which is 0.5 amps. Okay, so we have our I1 and our I2, but we need to find the Thevenin's voltage now, because we only have the Thevenin's resistance. So the Thevenin's voltage is the voltage here at that node. So if you pick this, which is this one here, we can do Kirchhoff's current law, which says that current entering a loop is equal to the current leaving a loop. So you have a current entering from that point, which is this one, another one entering from this point, which is this one, and then we can assume this one is leaving, which is that one there. So with our KCL there, current entering here will basically be the voltage, which is this one, minus the voltage there, which is Thevenin's voltage, divided by that resistance. You have that. Then the other current entering here is basically this same 2 amps is going there. Here is nothing, it will not go there. Then you have the current going down there, which is Thevenin's voltage there divided by the resistor involved. You're having that. Simplifying this one and solving for VTH, you are having Thevenin's voltage as 30 volts. So we have those, the Thevenin's voltage and the Thevenin resistance being those. If you put them in the circuit, you are going to have that. And then now the question was saying, hence find the current through the load. So the current there, you can use 2 methods. If you want, you can use voltage divider rule. You've got this supply voltage dividing between this resistor and that resistor there. So when you do a voltage divider rule, once you have the voltage going there, you have the voltage and the resistance there. It will be very easy to find the current. Or we know this is a closed loop. You can find the total resistance, which is basically this one and this one. That total resistance, when it divides into the voltage, you are going to have the circulating current in there, which is this one. So IL, or the circulating current in there, is basically the resistance, the voltage in here, divided by the summation of the oppositions, which is this resistance and the resistance there. So you have the Thevenin resistance, which is this one, and the load resistance here, which is this one, which was given in the question. Once we do our substitution there, you are going to have our load resistance as 3 amps. So in this example, I was using independent sources. We have 2 independent sources, the voltage source and the current source. The next example, we are going to have dependent sources. Let's look at the next example, the next slide. So here the question is saying, find the Thevenin equivalent circuit of the circuit in figure 8 at the terminals AB. So this is our figure 8 at those terminals. You can see you've got the independent source and the dependent source, which is this one. So for the independent source, when you switch it off, if it's a current source, it becomes an open circuit. But for dependent sources, these, you don't switch them off. Instead, what you do is you are going to excite this circuit with a voltage there, which you can give any value. But to simplify your calculation, it's better you give it 1 volt. Once you give it that, then you find the current flowing from that same source. And then you easily find the Thevenin's resistance. So from our circuit, which is this one here, we can see that the circuit contains a dependent source, which is this one. To find the RTH, we'll set the independent source equal to 0, just like I said. And then we'll excite the circuit with VO as 1 volt, which will just make us simplify calculations, but this can be anything. But our role is to find I0, which is this one here. So from our circuit here, we are exciting it with V0, which is this one here, 1 volt. It could be anything, but our role is to find the current flowing through that same voltage we've assumed. So in here, you've got 3 loops. You've got a loop here, a loop there, and a loop. Here there is no loop because we've switched off this independent source. So there will be an open circuit there. And then we do our loop analysis or mesh analysis. So in loop 1, once we do our analysis from loop 1, which is that one, if you're not comfortable with mesh analysis, you can go through the video I did on mesh analysis. I clearly explained how to find these expressions. So from loop 1, we are going to generate that equation. Okay, and Vx, it's been given polarities here. We are saying the positive and the negative. So this Vx is basically the voltage drop there. So this I2 is entering from the negative polarity. So therefore, this Vx is equal to negative 4 I2, which is this one here. So in here, where there was Vx, according to this analysis, we are putting this negative 4 I2. That's why it has become positive there. If you make I1 the subject, you are having this. And then if we analyze in the second loop, loop 2, which is this one, we give polarities again, going in the clockwise direction, giving positive to the first terminal you find. So for this one, you have positive, the other one there will be negative. For this one here, you have positive there, and that one there, negative down. So if we do our analysis in there, you're going to have this, which is the voltage in here should be equal to voltage drops in the resistors there. So this Vx as the exciter is equal to the voltage drop there. The voltage drop there is basically this resistance, which is 2, and then depending on the current. So this current is entering from the positive, that's why you have positive I2. That current there is entering from the negative. We are in here, so positive is here, negative is there. So this one will enter from the negative there, that's why you have got negative I1. For this resistance here, you have 6, which is this one here. The currents involved, I2 is entering from the positive, that's why we've got positive I2. But I3 is entering from the negative, you have this one here. From there, we know the value of Vx, which is this one here. If we substitute and simplify, we are going to get this equation coming to this. Okay, so in here where there is I1, we substitute with negative 3 I2. This is what you are having here. When you simplify, you are having this one here. From that, we are having this as our equation from our loop 2. And then loop 3 analysis, which is this one here. We assign polarities again, going in a clockwise direction. So we are meeting this terminal first. This one will be positive, that one will be negative. You meet this one first, this will be positive, the other one will be negative there. If we do our analysis, we're going to have this. So for this one, which is 6, we've got I3, which is positive, I2 will be negative because it's entering from the negative. Then you go 2 there, which is this one, and I3 because there's just one current passing through there. This is what you are having there. And then it's meeting this one here. This is just 1 volt as a voltage there. So from there, if you do our simplification in loop 3, we are having that as our equation. Now if you solve these two equations simultaneously, because we've got this one which has got I2 and I3, and this one I2 and I3, once you solve them simultaneously, you're going to have I3 because that's our interest, circulating current in there. I3 is going to be negative 1/6. I3 and I0 are related because I3 is basically I0 except I3 is moving in the clockwise, I0 is in the counterclockwise. So if I3 is positive, I0 will basically be negative. Or if I3 is negative, I0 will be positive. So this is what we are having there. I0 will be negative of I3, which is basically that. And now for us to find Thevenin's voltage, Thevenin's resistance, it will basically be the assumed voltage, which is 1 volt, divided by the I0, because our role was to find the I0, which has been this. When you divide this one into that one, we are having 6 ohms as our Thevenin's. So to find the Thevenin's voltage, it is the same circuit which we had. We are finding now, as we are viewing from there, the open circuit voltage, which is the voltage drop there. So we do our analysis in those 3 loops, loop 1, loop 2, loop 3. Previously we got this one 1, this one 2, this 3. Here we're calling this one 1, 2, that one 3. That's not a problem. So if we analyze from loop 1, we realize that the circulating current in there is just basically equal to the source current, which is 5. So we have that. And then if we come to loop 3, which is this one, we assign our polarities. You have those as you are going clockwise. So the first one you meet is this one, so that one will be positive, this one negative. Then if we analyze from there, we are going to have, because we are meeting this one first, that's the -2, that. And then when you come to this one, you're going to have this. This being simplified, it will give us that equation. When you go to loop 2, which is this one here, you assign polarities and you do our mesh analysis. We are having that. So we are having this as our equation. So relating this, because we know what Vx is from that one, where there is Vx, if you put that one, we are having that. And if we simplify that equation, we are going to have this giving us that. And from there, we have 2 equations. You've got this one and you've got that one. If you solve them simultaneously, we are going to have I2 as that. Thevenin's voltage will now be, that's the voltage there, to be the current passing through there and the resistance there. That product will give us 20 volts. This will be our Thevenin's voltage. So our circuit now simplifies, giving us 1 voltage, which is the Thevenin's voltage, and 1 resistance, Thevenin resistance, as we are viewing from the open circuit voltage there. Then this is the transformation we are having. Thanks for watching.